Hello everyone, my name is Ehsan Kazemivalipour. I will be presenting our work based on Eigenmode analysis of the S matrix. We received research grants from Aselsan. Transmit array or TxArray technology can be very critical since they can enhance field uniformity, increase power efficiency, and they can enable RF shimming while mitigating Sarhat spots. Increasing the number of independent transmit elements can enhance the TxArray coil's capabilities. However, for a higher number of array elements, the design complexity and high-power RF amplifiers cost will increase. Conventionally, the vast majority of studies concentrated on minimizing the magnitude of scattering parameters to tune, match, and decouple TxArray coils without considering the excitation signals. Excitation signals have a significant role in determining the total transmitted power levels. For a given TxArray coil, the reflection can be high for some excitation signals, but low for others. In this study, we introduced the concept of Eigenmode analysis. Looking at this matrix as a whole, we categorized the operation excitation modes as efficient and inefficient. We minimized the total reflected power for larger set of excitation signals. For a TxArray coil, this matrix is defined as the relationship between A and B, or vectors of the incident and reflected waves. The net transmitted power can be quantified as the difference between the total incident power and total reflected power. A perfect design has no reflection, which is not feasible when the elements are coupled. We define the normalized reflected power, or lambda, as the ratio of total reflected power to the total incident power, where it can be minimized to ensure high transmit efficiency. Suppose that lambda n and qn are the ion value and corresponding ion vector of S Hermitian S. If the coil is excited so that the excitation signal is equal to qn, then the normalized reflected power will be equal to lambda n. The ion vectors are orthogonal and represent the excitation vectors of the TxArray coil. Therefore, they can be called the excitation ion modes, and the ion values can be called the modal reflected power values. The normalized reflected power for any arbitrary excitation can be easily calculated as the normalized weighted sum of lambda n values. Ion modes form a unique orthogonal basis for all possible operation modes of TxArray coils. Any excitation can be decomposed into a superposition of ion modes. Also, all ion values are positive real with values less than or equal to 1. By sorting them from the smallest to the largest values, the normalized reflected power values are sorted when their corresponding ion vectors are applied to the coil as excitation signals. The ion modes with high lambda n values hardly contribute to the transmission process and to a certain degree can be considered inefficient and non-existent. Categorizing the ion modes limits the excitation space to a subset of ion modes. This limit should be defined by the hardware limitations. The knowledge of the efficient excitation space enables the user to achieve a proper shim more rapidly. Based on all these facts, the ion mode analysis provides insight to determine the optimum number of transmit elements in the design process. Increasing the number of efficient ion modes can expand the excitation space of TxArray coils. Also, there seems to be a limit in this. The coverage of this space can be modified. The proposed model and schematic of the 8-channel TxArray coil at 3 Tesla are shown here. In each loop, 5 capacitors mainly control the coil's performance. When the coil is derived in the CP mode, it produces a B1 plus field similar to a conventional birdcage coil. To find the capacitors, we minimize the normalized reflected power for ion modes and the CP mode, or lambda CP, as the lambda opt strategy. Minimizing lambda CP provides the opportunity to compose the CP mode from the most efficient ion modes. After designing the 8-channel coil, the results show that all transmit channels are very well matched. The maximum coupling is minus 12.3 dB. Also, the coil is properly tuned, matched, and decoupled. One of the ion modes has a very high reflection. If the coil is excited in this mode, only 1% of the incident power will be transmitted. Therefore, looking at the magnitude of S matrix is not sufficient to determine coil's transmission capabilities. On the other hand, the coil has 7 ion modes with less than 13% reflection. Also, in the CP mode, 9% of incident power is reflected. In the coil design process, it's possible to minimize lambda CP more. Also, this will increase the average of lambda n values. Here, the 8-channel coil was designed based on the lambda opt approach, where lambda CP was restricted to less than 1%. The results show that all matching levels are less than minus 14.5 dB. The maximum coupling is increased to minus 10.8 dB. Similarly, one ion mode has a very high reflection. the coil has 7 ion modes with less than 45% reflection. As we design, lambda CPs decreased to 1%. However, the average of lambda n values, or lambda average, was increased by 17%. This slide shows the normalized B1 plus patterns of all 8 ion modes and the CP mode for the 8-channel coil at 3 axial planes shown here. The B1 plus patterns are sorted from the ion modes with low reflection to high reflection. The first 7 columns show a reflection less than 45%. All their combinations also will have a reflection less than 45%. However, the B1 plus patterns of ion modes number 8 should not be considered in the RF shimmy process since it has 98% reflection. The results indicate that the first and second ion modes produce linear fields that are perpendicular to each other. The field generated by the CP mode mainly combine these two field patterns. To validate the simulation results, the 8-channel coil was constructed. The results show both simulated and measured coils resonate at the desired frequency with acceptable matching levels. The fabricated transmit elements are properly decoupled with a decoupling level greater than -10.6 dB. The lowest value of lambda average for both coils is less than 0.27 attained at the desired frequency. This figure shows that the manufactured coil also has 7 ion modes with less than 56% reflection. Besides, both simulated and measured lambda CP values are less than 11%. To evaluate the performance of the lambda opt strategy, we implemented one of the most commonly used design methods, which minimizes the S matrix elements to find the capacitors of 16-channel coil. Note that the trace of S Hermitian S is proportional to lambda average. Therefore, this approach minimizes lambda average by limiting the reflection coefficient to be less than -15 dB. After designing the 16-channel coil, the results show that in the lambda opt approach, all matching levels are less than -10 dB and the maximum coupling level is less than -6 dB. While in S-opt approach, the matching level are less than -15 dB. However, the maximum level of coupling is increased. For both approaches, 7 ion modes have a very high reflection. The dimension of efficient excitation space for both approaches are the same. In the lambda opt approach, the coil has 9 efficient ion modes with a reflection less than 42%, while in the S-opt approach, the reflection of the first 9 ion modes are less than 65%. In the S-opt approach, the average of efficient ion modes is 58% more compared to the lambda opt approach. The results also demonstrated that the solution obtained by the S-opt approach increases lambda CP by 15%. To conclude, I should say that in this study, we presented a technique based on the ion mode analysis of S matrix to obtain efficient operation modes of TxArray coils. Ion mode analysis provides a quantitative and compact representation of the coil's transmission capabilities. This method also provides insight into the excitation modes with low reflection. We introduced the concept of modal reflected power and excitation ion modes. By minimizing the modal reflected power values, we designed an 8-channel coil to have a low reflection for 7 dimensions of the excitation space. The same minimization on a 16-channel coil enabled us to have 9 efficient ion modes. For this coil, we illustrated that the low normalized reflected power for the CP mode could be achievable, although this coil is not very well matched and decoupled. If this coil is designed with a common design technique, the excitation space dimension is not changed. However, the average of efficient ion modes increased. Verify that our approach has a better performance. Thanks for your attention.